In episode 7, I'm going to go through what I don't understand about insulators and conductors as a chemistry teacher, physics teacher who's taught physics and chemistry for 13 years. What do I still feel like I don't understand? So this would be something that's a conductor, this would be something that's an insulator. I feel like I don't have a full conceptual understanding of what's going on at the particle level when I'm in contact with both of these. So I'm obviously at a different temperature than these. These have been sitting on the room. When I grab this feels slightly cold. When I grab this feels slightly warm. So the explanation there is that energy is going to this faster from me than it is to this. What I don't understand is, what is the reason why an insulator, when the particles in my skin are in contact with it, that there's less energy transfer? So I want to walk through a couple of examples of what I might be thinking. And I would say that not all insulators are like cork. Cork is very light, so here's another insulator that's quite a bit more massive. So I want to look at some potential things that might be going on, what I know, what I don't know. So when I have my finger particles in contact with an insulator, I kind of have a couple ideas. One is that the particles are spaced differently. So a lot of insulators are composed of a lot of air, things like foams, where they've spaced apart the solid particles in a way that somehow has put something in the middle of them. I don't really know or fully understand the structural components of them. Maybe there's some kind of long polymer, whatever. But at the end of the day, when I have contact between my particles, I have my skin particles, let's do those in red. Not all of them are in contact with the surface particles in the insulator. So if that's my finger, and then this is my finger, then when I'm touching the conductor, there are more particles in contact between the finger and the conductor than there are between the finger and the insulator. And so therefore, these particle collisions with these speed them up just the same as this one with this one, but this one is not being sped up, or slowed down when these collide, because these have nothing to collide with. I'm not fully understanding how I would have such a spacing in here, whether there's a long particle and so there's a gap in between the structures, or how that kind of works. But I could see a potential way in which this would kind of work. Or alternatively, I could see a way where the insulator particles are just the same spacing as a conductor set of particles, but for some reason, when there's a collision happening, that these collisions somehow transfer less energy to here. So I can think of a couple things that might influence that, but I'm not sure which are true and which ones even kind of fit into the whole physics, Newton's laws of motion. So I don't know if these particles have different masses, and somehow that affects the collisions. I don't know if these particles hit these ones and these ones speed up or slow down accordingly, but then somehow the transfer to the next set of particles takes longer. And I have a hard time with that one in particular, because I feel like in terms of conservation of energy, that any energy transferred here has to transfer to here, has to transfer to here. The way the particle collisions are happening, the same number of collisions should occur. So I don't really have a good understanding of how it's possible that this can collide with this and yet somehow less motion is transferred. This one I think makes a little bit of sense, but I've got some holes, not just in the structure here, but in kind of my understanding of how that structure differs. And then additionally, it could be a situation where there's far fewer particles because it's a lower density, something with mass might be involved there. Whereas when a conductor, we'll kind of go through and say, I feel like I have a solid understanding that these particles are moving, these particles are moving. They're moving at different average speeds, or different average kinetic energies really. And so when these collide with these, that on average we're seeing a speed up of these and a slowdown of those. I do feel like when I was in physics in college that there was kind of a temperature at the interface, and then there's kind of a temperature at the other interface, so there's something going on over here, maybe it's in contact with air, or maybe a table, and that there kind of is a gradient from the two temperatures from here to here, and this temperature has to match the temperature at the surface of this temperature has to match the temperature at the surface of this. So I don't know if it's that the motion is somehow getting lost in translation from this side to this differently. If it is, I really struggle with what does that mean about the collision. So this collides with this, then this collides with this, and this collides with this. So is there some way that there are less frequent collisions in a solid or a liquid that causes that heat transfer to be less? Does it somehow disperse greater in the medium? I feel like even if it disperses differently, that it should still end up. So one of my kind of underlying struggles is this a kinetics issue? Where it's about the transfer of energy in terms of rate of transfer? Or is it just a full amount of energy, that there's less energy, so it's a kind of a specific heat capacity issue? So for example, to heat a cork up might only take a certain number of joules. This might take very little energy. So from here to here, to get these up to temperature might take, let's just say 10 kilojoules. But for the conductor, I might require a much greater amount of energy. That might take me 80 kilojoules. So is it more energy is needed because there's more particles or more mass of the particles or something to that effect? Or is it, no, both of these can take 80 kilojoules to warm up, but this one takes a lot longer. So I feel like when I teach, frequently I go between the two, where I'm talking about rate of heating, or sometimes I'm talking about total amount of energy. And I'm not necessarily clear on when those become inappropriate. Frequently I can figure out when one is appropriate, but is that acceptable to say either, or is one more appropriate than the other? Another example of something I know is that if you have a window, and here's the outside of the window, and here's the inside of the house, that the type of gas you put in here can change how well of an insulator it is. And the way that it works is, so for instance, I'm going to do green particles here. We will call those neon, and we'll call the pink ones argon. So the argon is a bigger particle, and so argon is actually better at insulating for windows than neon would be, because it's larger at the same temperature, they will move slower. And so let's say it's warm inside and it's cold outside. So when the particle hits the surface, it's going to speed up, and it's going to carry some of that energy over to here, where it's going to slow down and transfer that energy outside. So the reason why neon is a better conductor in this case is because it makes more trips back and forth in the same time period. So both of them pick up about the same amounts of energy each trip, but this one's only going to go back and forth a few times, while the green ones are going to go back and forth many times. So that I have a solid understanding of. I feel like I'm kind of thorough on that. When I get into solids and liquids and corks and rubbers and metals, I feel like my understanding just completely falls apart. Not falls apart, but I don't really know what's happening. Is it something beneath the surface that's affecting the rate? Is it just the total amount of energy is different, and we're looking at things with very low specific heat capacities because they're very low in numbers of particles? Is the particle spacing itself causing a slowdown in how the rate of transfer of energy and motion is occurring?